Let's continue with our discussion of correlation. Correlation is highly important to the statistical models we will study in the next chapter. On this slide, you see examples of scatter chart representations of correlation. We won't use these in the rest of this class, but I want you to see them anyways to get an idea what you might encounter in actual applications. Plot A shows a negative correlation. You'll notice the dots show a trend. The trend in this case is as X values increase, the Y values decrease. So drawing this red line through these dots here that represents the best fit to these dots is a way of expressing this trend. And notice that it has a negative slope. By the way, the method for finding a line of best fit through the points of the scatter plot is called linear regression. We won't use linear regression in this class, but you should know the name. Plot B shows the opposite trend. In this case, a plot B, we see that as the X values increase, so do the Y values. They tend to increase together. A trend line through these points has a positive slope. Now look at plots C and D. These are both two different ways that zero correlation can look. Plot C just has no trend at all. There's no line that we could draw through these that wouldn't just be arbitrary. Plot D clearly has a trend, and we could draw a line of best fit. However, in this case, the trend is that as X values increase, the Y values just stay the same. In other words, X just seems completely unrelated to Y. The line of best fit in this case is flat, and that means it has zero slope. The correlation scale goes from -1 to 1. So the strongest possible correlations are -1 and 1. Correlation can't be any stronger than that. Suppose you have just one electrical outlet in your house, and you have two appliances, say a toaster and an oven lamp. In this case, if your toaster is plugged in, your lamp is not. And if your lamp is plugged in, then your toaster is not, because you only have the one plug, or the one socket. So 100% of the time when the toaster is on, the lamp is off, and vice versa. This would illustrate a negative correlation of -1 between the toaster being on and the lamp being on. A negative correlation of -0.5 is pretty significant. An example might be hours of exercise and body weight. As a person exercises more, their body weight tends to become less, but different people have different results, so it's not a perfect correlation. These two measures, notice, are moving in opposite directions. The hours of exercise and body weight. So the more hours of exercise, the less body weight. Zero correlation means no correlation. An example of zero or no correlations would be, say, donut sales and the size of Mount Baldy. No matter how little or how many donuts get sold, the mountain stays the same size. A positive correlation of 0.5 is just as substantial in terms of the strength of the correlation as the negative correlation, -0.5, I just discussed. However, a positive correlation occurs. What makes it positive is that the two measures being correlated move in the same direction. An example might be eating donuts and body weight. As my donut intake increases, my body weight tends to increase. Finally, a perfect positive correlation of +1 is the maximum possible positive correlation. An example might be distance to a destination and the time it takes to travel there. There is a precise matchup between these two sets of measures. Each measure changes in precisely the same way 100% of the time, both increasing and decreasing together. In terms of marbles in a jar, an example of a perfect positive correlation of 1 would be the case where 100% of the red marbles are large, while 0% of the green marbles are large. In this case, knowing that you have a red marble is a 100% indicator that you also have a large marble. One feature of correlation is that it is symmetric. This means, for example, if being red is positively correlated with being large in some population of marbles, then being large will be positively correlated with being red. In the example on this slide, you see that whether we represent the population in terms of size with respect to color, or in terms of color with respect to size, we always end up with the same correlation. In this case, 0. Notice the two horizontal lines look like one continuous flat line all the way across. Notice also that the proportions in each representation are the same, whether of large red versus large green, or of red large versus red small. Okay, here you need to pay special attention. This is something we're going to make a lot of use of in the next chapter. Okay, once you have a distribution, one of these rectangle boxes, you can determine the strength of a correlation and also whether the correlation is positive or negative by subtracting the relevant proportions. For instance, in the first distribution, this rectangle here, we determine the correlation of large and red by subtracting the proportion of large red marbles from the proportion of large green marbles. In this case, that's 0.75, 75% minus 25%. This gives us a positive value of 50%, or 0.5, which is the measure of correlation between large and red for this first distribution. In the lower distribution here, this second rectangle, the proportion of large red marbles is 25%, while the proportion of large green marbles is 50%. Subtracting, we get 25% minus 50% equals negative 0.25. This is a negative number, which in this case means knowing the marble is red reduces the probability that it is large. Notice that the large marbles here, regardless of color, make up 15, so where are we here? There's 15 over here, 20 over there, so that's 35 out of 100 marbles. So that's 35% of the total population here is large for this lower distribution. If I tell you that I've drawn a red marble from the jar, and you have to guess whether it is large or not, now knowing that it's red, you will reduce the probability from 35% to 25%. In other words, red is evidence against the marbles being large. Okay, now we're going to talk about probability models. These give us a more sophisticated way to talk about probabilities, especially a way to talk about probabilities of generalized events. For probability models, instead of the term variables, we will use random variables. Probabilities are taken to be equivalent to proportions of the values of the random variables. The reason we are calling these models is that instead of considering or measuring a real jar of marbles as with simple probabilities, we are really here instead considering and measuring a mathematical representation of random events. I know that sounds scary, but believe me, this is easy once we get down to the calculations. Let's look at this example here. This is here, right? Wait, this rectangle rectangle is a distribution which we have divided into two variable categories. The random variable color has 4 different values: red, green, blue, yellow. The random variable size has 2 different values: large and small. Consider the event of randomly finding a red marble in this population. In terms of a probability model, we are asking after the probability that the random variable color takes a value red. According to this distribution, 100 marbles are red out of 200 total marbles. We could represent this event by this grid here, where each cell in this grid represents the possible event of just pulling a marble, any one of these 200 marbles. Out of 200 total cells in this grid, 100, that is 50% of the grid, is red. The probability is the same as this proportion, 50%. So we're still thinking about things roughly the same way as before, but just with more of a mathematical orientation, so we can represent things more generally. Not only can we determine the probability of simple events, but we can determine the probability of sets of events. We express these sets in English using the terms and, or, and given that to put together statements of kinds of events. Let's take an easy case first. Do you remember earlier we talked about what's meant by the term mutually exclusive? If two events A and B are mutually exclusive, it means it is impossible for some circumstance to be both A and B at the same time. For instance, assuming solid color marbles, as we have been, it is impossible for there to be a marble that is both blue and yellow at the same time. If this is the case for events A and B, that they're mutually exclusive, then we can use the simple addition rule to determine the probability of the event A or B by just adding together the probability of A and the probability of B. Let me just review what or here means. So let's say the probability of, say, pulling a red marble or a yellow marble, which are two mutually exclusive events. What this means, but just in general, the probability of pulling an or. Let me back up. Forget about mutually exclusive. Let's just focus on the term or. What does or mean? So the event A or B can be true in 3 different cases. It can be true when just A by itself happens. It can be true when just B by itself happens. And it can be true when both A and B together happens. So there's 3 different ways that an or statement can be true. But in this particular case of the simple addition rule, we're essentially eliminating the third possible case of an or statement being true, that is, where A and B happen together. So in the case of the simple addition rule, where we have mutual exclusivity, the only way that it's going to be true, the or event is going to be true, is just if A happens by itself or if B happens by itself. So we can calculate that by just adding those 2 probabilities together. So the probability of blue or yellow being pulled from the marble, in other words, the probability of pulling either a blue marble or a yellow marble from this particular jar of marbles represented by this distribution, is the probability of pulling a blue marble, which is 30 out of 200, plus the probability of pulling a yellow marble, which is 20 out of 200, which is 25%. Okay, here we're introduced to the simple multiplication rule for dealing with AND statements. So let me just pause for a minute and talk about what's meant by an AND statement. The event A and B is true just in one case, where both A is true and B is true at the same time. So there's very different truth conditions on an AND event than there are, than there are for an OR event. Okay, so so here we're being introduced to the simple multiplication rule for dealing with AND statements. You can use the simple version if A and B are not correlated. For red and large, not being correlated means the proportion of large among the reds is the same as the proportion of large among the marbles of any other color. So notice here that you have 50% of the red marbles are large, 50% of the red marbles. See, 50 out of 100 of the red marbles are large, 50 out of 100 red marbles are small. Here you have also 50% of the green marbles are large, 50% of the green marbles are small. Here you have 50% of the blue marbles are large, 50% of the blue marbles are small, and again 50-50 for large and small among the yellows. So in every case you have a proportion of 50%, which means that knowing the color of the marble isn't going to be any kind of an indicator for whether it's large or not. So so you have a case of no correlation. So where that is true, that you have a case of no correlation between the events or properties A and B, then you can use the simple version of the multiplication rule. So for example, for red and large, these are not correlated here. Red and large are not correlated, which means the proportion of large marbles among the reds is the same as the proportion of large marbles among those of any other color. So because large and red are not correlated, then the probability of a marble being both large and red is just the product of the probability of its being red times the probability of its being large. So in this case, that's the probability of being red is 100 over 200 times the probability of being large, which is 100 over 200, which is 50% times 50%, which is 25%. Conditional probabilities are used when we want to know the probability of some event when some other event is known or assumed to be true. For instance, the probability of breaking your leg is 1 in 500, or 0.2%. However, the odds of breaking your leg, given that you regularly engage in extreme sports, is at least 10%. That's 50 times higher. So that's a very important piece of information to know if we're trying to determine the chance that you're going to break your leg. And so that changes the probability. Okay, so in the case of marbles, if we want to know the probability of having pulled a large marble given that it is a red marble, this is written this way. See with this line here between large and red. And it's red, the probability of large given that it's red. That's how you say this. The probability of large given that it's red. And this means you know or assume that a red marble has been pulled, and now you are trying to calculate the probability of its being large in the light of this piece of knowledge or this assumption that it's red. So the probability of a large marble will be proportional to the red marble the subpopulation, and not to the population as a whole. So you calculate this conditional probability by putting the number of large marbles as the numerator and the number of red marbles as the denominator, right? Not the total population, but just the number of red marbles as the denominator. So that comes out to 50%. See, right, you have 50 large marbles among the reds. So if you know that a red marble has been pulled, you don't care about green, blue, or yellow marbles anymore, right? You know that one of these 100 marbles has been pulled if you are being told that a red marble has been pulled. It's one of those 100. So the probability of it being red, the probability of it being large, given that it's red, is this 50, one of these 50 large marbles among this subpopulation of red marbles, which is 50 over 100 or 50%. Okay, now let's talk about the general multiplication rule. And this works for any and statements, whether correlated or not. Notice I've changed the color of the table here from blue to orange to indicate that this is a different jar of marbles than before, with a different distribution. In this case, you'll notice red and large are correlated. So if we want to know the probability of pulling a large red marble from this jar, we need to use the general multiplication rule. To determine this, multiply the probability of pulling a red marble by the probability of pulling a large marble given that it is red. So let's see how we do this here. So this is a general multiplication rule for any and statements. So the probability of, let's see, in this case we're looking at the probability of red and large. So in other words, the probability of pulling a large red marble is the probability of pulling a red marble, right, which is 100 out of 200 total, so that's 50%, times the probability of pulling a large marble given that it's red, so that's 80 out of 100, right, the 80 large marbles out of the subpopulation of reds, 100, so that's 80%, and then multiplied together that gives you 40%. Here's another way of picturing this idea of conditional probability, the probability of B given A. So let's say that A is true. Let's say that A happened. Okay, so that means everything in this circle, A circle, has happened. You want to know the probability of a B event in the light of the fact that A happened. So in terms of these Venn diagram circles, that means this part of the B circle inside of the A circle. See, this is this overlap area. The overlap area is the part of the B circle that's inside of A. So if A happened, it includes this little chunk here of B, which is the intersection of A and B. Okay, here's another example. I have 4 tomato products, pizza sauce, pasta sauce, V8, and ketchup. And I have 4 condiments, ketchup, mayonnaise, soy sauce, and mustard. Suppose I tell you I have a tomato product. Okay, so now you know I have one of these 4, a tomato product. What's the probability of this tomato product that I have? Let's say I don't tell you which tomato product it is. I just say I have some tomato product. It's one of these 4. What's the probability of it being a condiment also? Well, notice that ketchup is the only one of these 4 tomato products that's also a condiment. So it's this one now, this one condiment out of the total population of tomato products, 4, that is the probability that the tomato product I have is also a condiment. So that's 1 out of 4, 25%. And notice again, ketchup is in the intersection of this Venn diagram. Okay. Finally, let's talk about the general rule for calculating the probability of OR events, whether mutually exclusive or not. In this case, you have to avoid the possibility of double counting events in the intersection. Remember, the event of A or B can occur if A happens by itself, if B happens by itself, or if A and B happen together. But A by itself or B by itself each include whatever's in the intersection of A and B already. So we need to subtract that intersection to avoid counting things twice. The intersection is, in this case, A and B right here. So here's the formula for the general addition rule. For any OR events, determining the probability of any OR events, it's the probability of the A event by itself plus the probability of the B event by itself minus the probability of A and B. So in a couple slides ago, we calculated the probability of red and large as 40%. So that makes it easier to solve this one. So the probability of red or pulling a red marble or a large marble from this jar of marbles is going to be the probability of pulling a red marble, which is 100 out of 250%, plus the probability of pulling a large marble, which is again 100 out of 250%, minus the probability of pulling both a red and a large marble, which is 40%, and so that's 100 minus 40, which is 60%. And here's just I'm not going to read through all this, but you'll just see visually, right? If you have two events and you're trying to figure out what's the probability of event A or event B, you'll notice we have two events here in event A, and we have three little events that make up set B. So let's call these sets. Okay, we have set A, which is made up of two events. We have set B, which is made up of three events. And so we want to know the probability of A or B. Well, we don't want to just add these together, because you'll notice that this event HT and this event here HT, it's the same event. So if you just add these together directly, you're going to end up with too many things. You're going to count HT twice. So you want to make sure that you take out the extra HT in this case. So when you represent it this way with HT in the intersection, you can see clearly better how to add these things up. And so that's why we need to, in the general formula, to subtract the intersection so we don't double count. Okay. Hope that was informative.